All right, everybody. We're going to get started. I see that there are still a few people who have not joined the activity yet, and that's okay. Please join the activity when you can. If you need the link again, please let me know. I'd be happy to drop it back in the chat again or directly to you. Just let me know. But we're going to get started. I'll take a look at all of what you guys had to say in your check-in and such after class when I have time to. But for now, we're going to get started. All right, so first, and I'll just be adding screens that you guys are able to go through along the way here. So we're moving on to screen number 2, which is our objectives for section 9.2, tests about a population proportion. All right, similar to the last few chapters, we do like a general idea, significance tests, and then we go look at proportions and then means. Today we're dealing with proportions. Right. After this section, you should be able to state and check the random 10% and large counts condition for performing a significance test about a population proportion. Perform a significance test about a population proportion. Interpret the power of a test and describe what factors affect the power of a test. And describe the relationship among the probability of a type 1 error, probability of a type 2 error, and the power of a test. All right, these are the things we're going to go for today. We will not get through all of these today. We'll finish up some after spring break, which will be fine because we'll need to review this after spring break anyway. So we'll get through like half of this today. So first, check conditions. All right, these are the same 3 conditions we saw in chapter 8. All right. So again, in chapter 8, we introduced 3 conditions that should be met before we construct a confidence interval for an unknown population proportion: random, 10% when sampling without replacement, and large counts. These same 3 conditions must be verified before carrying out a significance test. All right, same thing, same as in chapter 8. All right, we have to check that it is random. The data come from a well-designed random sample or randomized experiment. 10% when sampling without replacement, check that the sample size n is less than or equal to 1/10 of the population size, capital N. Okay. Large counts, both NP sub 0, which is just the proportion of our null hypothesis, and n times 1 minus p sub 0 are at least 10. All right. So it's the same 3 conditions that we used in chapter 8 for proportions. I see we need a moment to write anything down for their notes. Please raise your hand. All right. So then we get to our first little problem here. Walking to school. A recent report claimed that 13% of students typically walk to school. Deanna thinks that the proportion is higher than 0.13 at her large elementary school, so she surveys a random sample of 100 students to find out. Are the conditions for carrying out a significance test met? Yes or no? After you select your choice of yes or no, you will be prompted to provide an explanation. All right, so please take a moment, answer the question, and provide a reasoning as to why you made your choice. And we'll talk about it in just a few minutes. Okay, everybody, we're going to talk about this one. Hopefully you had a chance to make a choice here and begin your explanation. At minimum, I hope you decided whether or not the conditions were met. It does look as though most of you guys think that it is yes, the conditions are met. There's a few people who believe no. Some of those people are switching to yes. And so, remember, when we're talking about the conditions being met, right, the only conditions we're checking are those 3 things. Was the sample random? Are we using less than 10% of the population in our sample? And is the large counts condition satisfied? Because we need the large counts condition satisfied so we can use our standard normal curve. All right. Anything outside of those 3 things we don't really have to consider at this point. They could be reasons why later on that we may have an error or a sampling error, or could explain why we got a certain type of result. but at this point we're only checking these 3 specific conditions. Right? And in this case, yes, the conditions are met. Right? And the reasoning here, the conditions being checked, we have right here on my OneNote page. So random, this sample was a random sample. We were told that in the context, so we can just say, hey, it's a random sample, excellent. 10% condition, the sample size of 100 is less than 10% of the school's population. And again, we can say this because we were told the population of the school is large. We weren't told exactly the number of students, but it's safe to assume at this point that there's over 1,000 students in the school because it's large. So 100 is less than 10%. And lastly, the large counts condition. 13% of 100 is 13, which is greater than or equal to 10. And 87% of 100, which is the rest of the population or the rest of the sample size, is 87, which is greater than or equal to 10. Since the number of successes and the number of failures are both greater than 10, large counts is met, we are good to proceed. Right? These things have to be checked to allow us to do the type of inference we're going to do with, we'll see next, right? Our Z statistic, as we'll call it. All right, is there anything I can clarify about this first example? Okay. Next screen, what is a significance test? We kind of saw what this was in section 9.1. So we're going to continue on that thread. A significance test uses sample data to measure the strength of evidence against the null hypothesis. All right, essentially, we're always trying to find evidence that disproves the null hypothesis. That's what we're going for. Here are some principles that apply to most tests. The test compares a statistic calculated from sample data with the value of the parameter stated by the null hypothesis. Values of the statistic far from the null parameter value in the direction specified by the alternative hypothesis give evidence against the null hypothesis. Right? So if our alternative was that the proportion is actually greater than the null hypothesis, if we find values that are less than the null hypothesis, that's not evidence against because it's not in the direction specified by the alternative. Right? A test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis, H sub 0, were true. In standardized units, that is, test statistic equals statistic minus parameter divided by standard deviation of statistic. Right? And essentially, we're finding different ways to write standardized scores using different situations. Right? In this case, we have the statistic from our sample, the parameter from our null hypothesis, and the standard deviation of the sample. Right? Continue. Does anyone need a moment to write anything down from this screen? So this gets the Z statistic. When carrying out a significance test about a population, we will use the test statistic of a Z statistic. We call it a Z statistic because it is similar to a Z-score and will be used along with table A to help find the p-value for our significance test. It makes sense. It's following along with stuff that we've seen previously. All right, the Z statistic is Z equals p hat minus p divided by the square root of p sub 0 times 1 minus p sub 0 divided by n. And I forgot to fix my notations here, so I apologize, but where p hat is the sample proportion, p is the parameter value, and p sub 0 is the null hypothesis parameter value. Typically, p and p sub 0 are the same value. I'm not going to spend too much time on the screen because the next one has like our formal definition with the same formula on it. losing people. Oh, sorry. So we get the one sample Z test for a proportion. This is our inference method for a significance test. Right? Just like we had our inference method for confidence levels, confidence intervals. Right? This is the one that we use for significance, or one of them. One sample Z test for a proportion. We're going to choose an SRS of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis h sub 0 such that p equals p sub 0, compute the Z statistic. Z equals p hat minus p divided by the square root of p0 times 1 minus p0 divided by n. It is very important when you make notation for this that that is a subscript 0 and not just a 0 next to the p, because 0 next to the p implies multiplying by 0, and that means 0. So be careful with your notations. Find the p-value by calculating the probability of getting a Z statistic this large or larger in the direction specified by the alternative hypothesis, h sub a. And so we get these little normal curves here at the bottom. Right? If the alternative is that p is actually greater than the null hypothesis, we're looking at the area under the curve greater than Z. If the alternative is that it's less than the null hypothesis, we look at the area under the curve less than Z. And that we just use whatever Z is. It could be positive, it could be negative. Depends on what we get from our formula. If we have a two-sided hypothesis, right, where we're just saying p just is not the same as the null hypothesis, then we get a two-sided graph, so to say. We're looking at both tails. Less than, the area under the curve less than the negative Z, and the area under the curve greater than positive Z. The nice thing is in a normal curve we have symmetry. And so if I find one of these with the area less than negative Z or the area greater than positive Z, I just multiply it by 2 for the p-value. I do not need to find them both separately, just multiply by 2. Okay. So you need a moment to write anything down. Please raise your hand. All right, so then our next example problem, which draws on what we just did with slide number 4 about walking to school. And now we have some sample data from our sample of 100 students. All right, for Deanna's survey, 17 students in the sample said they typically walk to school. All right, we want to calculate the test statistic, right, which is using that Z equals formula, and then find the p-value using table A. I have a link to table A right here. It is also all the other formulas and stuff for that you'll find on the AP test that are provided, but you'll also have table A in there, so that's why the link is here. A suggestion here, I recommend doing your work on paper and then uploading a picture of your work using the upload image icon option down here. Or you can simply use the text entry box to type in your results. That is up to you. All right. I don't see any hands. So we're going to talk about this, guys. I know that this was probably a little tough, and that's okay. This is just our first time trying this stuff. So let's look at what it is. All right, I'm going to show the work here. Please, I encourage you guys to follow along with what's going on in the shared screen. All right, so part A, we're finding the test statistic, the Z statistic. Right, and so I have the formula here for the Z statistic is Z equals p hat minus p divided by the square root of p0 times 1 minus p0 divided by n. The hypotheses that we're testing is the null hypothesis that p is equal to 0.13 versus the alternative hypothesis that p is greater than 0.13. Our sample proportion p hat is 17 out of 100, which is 0.17. P is equal to P sub 0, which is 0.13. So we now have everything we need to find our test statistic. We get Z equals 0.17 minus 0.13 divided by the square root of 0.13 times 0.87 divided by 100. If you're punching this in your calculator, you may want to put parentheses around this division that's under the square root sign, because you're taking the square root of that entire thing. Ultimately, we get 1.19 after a little bit of rounding. I think it's like 1.188, so we'll just round it to 1.19 because we only get 2 decimal places for table 8 anyway. So that's our test statistic. Is there any questions about how we got the test statistic? So then the next part, part B, right, we're finding the p-value. All right. The p-value is the probability that Z is greater than 1.19, and that's based on our alternative is saying that we are greater than the null hypothesis. So what's the probability they get a Z score greater than 1.19? Well, that's equal to the probability of getting 1 minus the probability of Z being less than or equal to 1.19. We have to do this step because table A only gives me less than values. It's not going to tell me the proportion under the curve greater than a certain number. It only tells me less than. So we then find Z, the Z score of 1.19 on table A. We find 1.1 over here along the left-hand column. 0.09 on the top row. They intersect right here at 0.883. So we do 1 minus 0.883, we get 0.117 for our p-value. Right. In the graph of the normal curve, this is the shaded red area here is the proportion greater than 1.19, and that is about 11.7%. Okay. And so at this point, we're done. We were not asked to make a conclusion about the p-value. We weren't asked to compare it to a alpha, like we weren't asked to compare it against a significance level and make a conclusion. So we're done. We were just asked to find it, and we did. There it is. Is there anything I can clarify about this part or any of this calculation? Okay. So the next, we just saw an example of a one-sided statistic or a one-sided test, but there's also two-sided tests, right? The p-value in a one-sided test is the area in one tail of a standard normal distribution, the tail specified by the alternative hypothesis, which is what we just saw. In a two-sided test, the alternative hypothesis has the form H sub A such that P is not equal to P sub 0. The p-value in such a test is the probability of getting a sample proportion as far as or farther from P sub 0 in either direction than the observed value of P hat. As a result, you have to find the area in both tails of a standard normal distribution to get the p-value. And again, this is what I was saying, where you find the area under one tail and then you double it because we have symmetry. Right, and the picture of kind of what that looks like is on slide 7 with our definition here. Right, the alternative hypothesis such that P is not equal to P sub 0, we have the two tails. Each tail occupies the same amount of area. All right. Now there's a nice connection here between our two-sided test and confidence intervals. Right? The 95% confidence interval gives an approximate range of P sub 0s that would not be rejected by a two-sided test at the alpha equal 0.05 significance level. All right, so essentially, if you have a 95% confidence level, any value you get in there will result in not rejecting the null hypothesis. Anything that lies outside that confidence interval, right, would then lead us to reject the null hypothesis. Okay, a two-sided test at significance level alpha, say alpha equals 0.05, and a 100 times 1 minus alpha percent confidence interval, 95% confidence interval of alpha equals 0.05, gives similar information about the population parameter. Right, they tell us a little bit more about what is reasonable or what's plausible. And we do keep seeing this alpha equals 0.05. That's kind of a go-to if you're not told what significance level to use 0.05. Otherwise, use whatever the context is telling you to use. All right. Now that we've got all the parts for conducting a significance test, we need to use the four-step process to perform a significance test. All right, to perform a significance test, we state hypotheses, check conditions, calculate a test statistic and p-value, and draw a conclusion in the context of the problem. Four-step process is ideal for organizing our work. It gives us steps to follow. All right, we start by making our statement. What hypotheses do you want to test, and at what significance level? Define any parameters you use. Right, and when they say parameters, p, mu, sigma, those are parameters. Remember, parameters are for populations. Hypotheses are always about parameters. Plan, choose the appropriate inference method, check conditions. Right? The only inference method we have so far for a significance test is the one sample z-test for proportions. Do, if the conditions are met, perform calculations, compute the test statistic, find the p-value. Those are the calculations. Once we have those things, we can then make our conclusion, make a decision about the hypotheses in the context of the problem. Remember, if the p-value is greater than alpha, that leads us not to reject the null hypothesis, and we do not have evidence to support the alternative. When the p-value is small, like smaller than alpha, less than, then we reject the null hypothesis, and we have evidence to support the alternative. That's when we make that conclusion, and we say something to that effect, but we put in the context. Okay. Is there anything I can clarify? All right. So that's where we're going to stop today. There is definitely more to this. There's a few more, so there's like 6 more slides I have in here, but we'll get to that as part of the lesson when we come back to school after spring break. Just for now, while I have you here, we'll take a look at the course. Right, we're in March. It's the 23rd. There's a link to our Desmos activity here. Right. There's also a link in the calendar to the actual PowerPoint presentation that would just be the presentation, not what we did here in Desmos. I will upload the solutions to the Desmos problems and a recording later. Also, if you look at chapter 9 in the modules, all the resources and notes are available for 9.2 and 9.3, as well as the practice problems and solutions. I highly encourage you to, if you have time, look at the resources and notes that are available in the module and try some of the practice problems, especially the ones from 9.1. Okay, we should be able to do those ones at this point. All right. And if you have any questions, comments, concerns, you need help with anything, you're working on assignments that are missing, let me know. I'm more than happy to help. But I can't help if I don't know. So with that, we're essentially done for the day. The next time I see you will be in like 2 weeks after spring break. So I hope you guys have a wonderful rest of your day, an excellent rest of your week, a fantastic weekend, and an awesome spring break. And we'll see you in a couple weeks.